Tim?
I think he's just popped it to the
He's
back.
just popped out, has he? So I hope he will turn up. So he's supposed to be taking notes. So our first speaker is Sarah Darby from the Environmental Change Institute, and she's going to talk to us about integration. So over to you, Sarah. Hopefully you can navigate the...
Super, thank you. All right, yes. Right. Good afternoon, everyone. I'm going to offer you a few thoughts that have come from recent experience working on the Integrate programme here at Oxford, which is just coming to an end this month, and the LEO programme, which is a big demonstrator programme, both of which have a lot to do with integrating renewables. So even at the start of Integrate, which was, I think, 2015-16, we were already getting into the happy position where renewables were becoming more and more competitive as a source of supply. And it was also becoming clearer just how important it was going to be in electrifying our system, our systems, not just in this country, but anywhere, to look at integrating renewables into a system and having a paradigm shift in how we look at our energy systems. So the move away from the old centralized hub and spoke mode, in which we also predicted, we think demand is going to be X, we will therefore build this number of generators, to a much more networked approach where you have distributed assets all over the place. So it's not just your demand, which is highly distributed. That's always been the case. It's always been local. But increasingly, your supply was becoming local and highly distributed as well. There were going to be changes in pattern and demand. There were going to be, and the amount of demand for electricity, especially with the electrification of heating and of transport. And there were also these changes in supply happening. And this was going to be quite a challenge to meet that. So Integrate was set up for that purpose. And LEO, in a sense, takes this on and looks at it in a very focused way in terms of Oxfordshire. Can you set up a smart local energy system that is run on renewables? So it's a sort of proof of concept project, if you like. And it's doing in real time with real people in a real place. It's trying to set up a smart local energy system, which means connecting up the technologies, the technology to technology connection, connecting up the people, the actors in the energy system, and connecting the people with the technologies so that you have technologies that people understand and know how to operate at all sorts of levels. So here I give you some headlines from the Integrate programme. So this is from the synthesis report, which you may want to take a look at afterwards. So as I say, solar and wind really growing in significance and importance, not just here, but around the world. And using them effectively is really going to depend very heavily on integrating variable generation into the electricity network, making it work for the network, not just putting more and more copper into the ground and having ever more, but managing intelligently the balancing of supply with demand, and moving from a demand-led system where you build new supply to meet the demand to a supply-led system where you use the available supply intelligently when it's there. And store it if necessary, but you try and do some active management of demand. And so any solution to this big challenge is going to involve a mix of having flexible, active demand, interconnection between networks, between scales, and storage. And that means a lot of work in quite a lot of areas, including the market design, the regulation of the system, and the governance of the system. So these were the headlines from that programme. coming to Project and this is how we visualized this sort of challenge. So this was at the outset of Integrate. We developed this portcullis. So down the left-hand side, you see the challenges as we saw them then. And along the top, you have the sort of drivers of uncertainty. So if you like, the problems, but also the opportunities. So we saw opportunities for flexibility, not just in the resources and the storage, but also in the customers themselves. Are people flexible? You know, what can be done to make them more flexible? And now that we've come to the end of Integrate, I think if we were starting again, I would add another 2 bars to that portcullis. So this is just my cheeky intervention, if you like. This isn't official, but I think I would also add in the crucial importance of infrastructure on the one hand, and of not looking at people just as customers, but as actors in the energy system. So often, you know, the standard sort of modeling, the only thing you're allowed to be as a person is a supplier or a consumer. But we all know we're more than that. There are all sorts of actors in the energy system, and I've listed some of them along the top there. You know, without them, the system does not work. Their behavior, their decisions matter a lot. I could talk about Leo for, when we then moved to Leo and Local Energy Oxfordshire, there are any number of things I could talk about, but I'm going to choose, as we're talking about integration, the integration of energy planning with land use planning. And this has been, I think, one of the big steps forward from Leo. It's been the development of a really sophisticated and helpful mapping system, really. And it has all sorts of different layers. So boundaries, why do we need to know about boundaries? Because of who is setting the rules within those boundaries. We also need substation area boundaries. Okay, so if you live within such and such a boundary, which substations are you attached to, secondary and primary? What's the mix of demand within that boundary? Business, leisure, residential, and so on. The planning environment, is it an area of special scientific interest? If it is, you can forget about putting a solar farm there, you know, that kind of thing. The electricity network boundaries, and what are the potential areas where you can site renewables in the county? And then there has also been aerial photography, this was mentioned earlier, where you can get an idea of where are the suitable sites, where are the roofs, the orientation, the pitch, where are the buildings that are leaking heat like mad, you know, and that urgently do need attention. So we developed I say we, I wasn't involved in this personally, but Leo, a lot of work has been done on developing this land use map, mostly at Oxford Brookes and with the County Council. And just to give you an example of just some of the overlays, I think, in fact, Peter Sudbury showed this earlier, but this gives you some idea of the sort of land area potential there is in Oxfordshire that would be suitable, in theory at any rate, you know, for solar or for wind, where the resource is there and there aren't the constraints that might apply that would stop it. For example, if you're in a conservation area, you're probably not allowed to put solar panels on your roof, or not on a roof that is visible from the street anyway. And then building on that, you add these in these other data sets, and you're really getting something incredibly high resolution and very, very powerful, thanks to the wonders of geographical information systems. So you can do all these overlays of the different maps to answer the sort of questions you might have about integrating renewables. And the aim a major aim from all this sort of exercise is that through doing this mapping on integration, you can enable local area energy planning. And in fact, the Energy Systems Catapult are bringing out a report on this today. They're bringing out more than a report, they're bringing out a local area energy planning tool. So this is the sort of work that is going into that. Because up till now, there's been very little interaction between energy planning and land use planning. So, for example, it's been quite possible to plan a development of 2,000 homes in Oxfordshire, and only this was in Aynsham, I think, and it was only towards the very end of that process, that they realised that the local network operator, Scottish and Southern Energy Networks, didn't actually know about this, and making the connection that was going to be needed for this, which immediately, of course, alters the economics of the thing. And you can imagine, so bringing these two together is becoming increasingly important. And so that's happening at one level. That's very important. Another really lovely thing that is coming out of this exercise is the use of these maps for communicating with the citizens of Oxfordshire. It can be a very engaging thing to be able to visualize what's going on in your area and to understand what the possibilities are. And the maps are being used in this way as well. Also, it's interactive, this mapping tool. And so you can use it in that way too. So you can go online, you can get into this. And you can try out different scenarios with it as well. So that's Baron, that's really all I wanted to say at this stage. I'd be very happy to answer questions later and talk about this. But I just thought I would flag up some programs you might want to look out for that are going on in this country at this time in relation to integrating renewables. Energy Rev is by far the biggest of them, because that is a really big academic program, which has, I think, 29 different universities involved in it. But there's a lot of interesting stuff going on in that. There are the LEO and the ESO demonstration projects in Oxfordshire, and their sister project, Reflex in Orkney. I can't be keen enough about demonstration projects. We all know in the academic literature, the thousands and thousands of papers that say, in theory, we model this, we think there is the potential to do that. The number of papers you can read that say, we tried doing this. This is what worked, and this is why. This is what didn't work, even more important perhaps, and this is why. It's a minuscule proportion of the whole. Demonstration projects, they're big, they're difficult, they're expensive, they're a lot of hard work, etc. But boy, are they worthwhile. So, I'd kind of encourage you to, whenever you get a chance, if you're interested in integrating renewables, go for the demonstration projects. Okay.
Thank you very much. Well within time. That's excellent work.
Right.
So we're going to move quickly on to the next talk, and then we'll come back for a bit of discussion. The next talk will be given by Tom Adcock, who is from the Department of Engineering Science, moving offshore or into the marine environment, talking about tidal energy. So over to you, Tom.
Thank you, Bowen. So I'm afraid I'm not going to be talking about demonstrators, and particularly not in terms of what I'm going to focus on in this talk. So as Bowen said, I'm an associate professor in the Department of Engineering Science, and the focus of my work actually is really on loads in the offshore environment and how we model those. And the main application for that at the moment is offshore wind. But our chair is going to be speaking about that offshore wind as a technology later. And so for now, I'm going to be talking about tidal power. So as I'm sure many of you are aware of some of the basics, where there are two sort of fundamental technologies that we are interested in tidal. One is essentially building big concrete walls across estuaries and essentially creating impoundments, and then using the rise and fall of the tide to drive flow through turbines and generate power that way. And saw in the news that renewed commitment from the Welsh Government for the big potential Severn barrage problem was being flagged yesterday. This is, from a technological point of view, most of the technology involved in this is pretty standard, but the big downside is the environmental impact and also the huge upfront cost of the technology. So that's led people to really focus on tidal stream. So this is just as tidal range is only really suitable in areas where there is a large tidal range. Tidal stream is again only going to be a practical technology in certain areas where there are very fast flowing currents. Fundamentally, a tidal turbine will look similar to a wind turbine, only in general the loading is rather higher, so the sort of blades look a bit different, and there are a number of other more subtle differences between the technologies in terms of actually just the thing that is generating the power. And attention is really turned on these because it's much easier to develop these incrementally, and these potentially have a lower environmental impact than building a big concrete wall across an estuary, although there is still some impact from such a technology. So the key advantage, which again I'm sure you're all aware of tidal compared to other renewables, and this obviously fits in very much with the more systems people who are here today, is that tidal is predictable. But tidal, and it is driven by the movement of the moon and the sun, and we know where those are going to be essentially indefinitely far ahead. But it is also intermittent. And it's one thing you see quite often is that they say, but the phase of the tide is going to be different as you move around something the size of the United Kingdom, and that helps to smooth out the resource. And indeed, that is true, but only to a certain extent. And the problem with that is essentially the fact that there's a spring neap cycle, that sometimes the moon and the sun are pulling in the same direction, and sometimes they're not. And that means you get a big variation in the power over a fortnightly cycle. And that's going to be the same, well, in fact, all over the world, not just all over a particular country. And so that, to some extent, undermines that smoothing argument. And that's something I am looking to look at in the next few years. And one of the key questions with tidal is, well, how much use is that the fact it's predictable, and how much, but intermittent. And yes, it's probably going to be expensive, but that predictability is worth something. But then the intermittency kind of takes away from that, and that's really the equation that we need to understand whether we go forward with tidal. So to turn to the Oxford work, so the main work that's going on at the moment in Oxford is at the turbine scale, which is being led by my colleague, Professor Wilden, who can't be here today. And particularly, he's looking at how we go from particular turbines and how we design for those, and think about how we turn those into arrays. So this is, although it looks a bit like a computer-generated image, this is actually some experiments that Richard and his team were doing in Edinburgh, looking at what happens as we have moved turbines closer and further apart. And he has a big theme of work looking at that and how we can essentially increase the power that we are getting from the turbines. But to me, I think I would argue that there is a more fundamental issue with tidal that we need to answer, which is how big is the tidal resource? And we need to think about this. I mean, whether tidal is going to be useful is not going to be whether we can get another 10, 20% out. It's going to be, is the resource really worth it to start with? And I've already touched on that in terms of thinking about how it fits in as a predictable but intermittent resource. So estimates for this is something I saw on LinkedIn a few weeks ago, where some company, who I must admit I'm not, were having, I think, quite a generous estimate for what the tidal resource, both of the world and the UK, might be. but certainly estimates out there for what the resource, say, of the United Kingdom, which is probably has the best resource of any country in the world. Well, they vary by over an order of magnitude. And that makes a big difference whether they're at one end of that spectrum or another about whether we should be pursuing the technology and how useful it is going to be. So what my group has worked on, and we're still doing some work in this area, is to try and help try and pin down this question. And coupled with this is how well this interacts with other less predictable but also intermittent renewable energy resources, and of course some of the questions that Sarah was touching on earlier. So the resource of a tidal barrage system, that's pretty well understood. That we have good models for what's going on there. Something like Severn barrage, we know that on average that's going to be about 2 gigawatts. Depends a bit on how you design the detail, but we're pretty clear on orders of magnitude that we're going to get out there. But other barrages would be much less and really wouldn't contribute much, at least at a national scale. They might be important locally, but at a national scale, the Severn barrage is the key thing. I'm going to talk a bit more about the tidal resource, and this is sort of, the tidal stream resource, which is primarily what my team look at. So the best site probably in the world, certainly in the United Kingdom, is the Pentland Firth, and this is a numerical simulation of the flow going backwards and forwards in the Pentland Firth. And this is the sort of thing that we develop, and then we look at how energy comes out, how we would extract energy from such a system. And what I'm going to do is I'm going to try and talk you through this graph. So this is a bit probably simplified compared to the Pentland Firth, but what we try and do for the more complex real sites is try and do a similar analysis to the one that I'll talk through now. So with wind, which you're probably more familiar with, if we put some turbines in, we're starting to get really big wind farms which have an influence on what the wind is, but it's still really quite small. It's still a few percent. It's not a big change to the wind, but that's different with tides. If we put some tidal turbines in a flow, it slows it down. So we have a significant feedback, and as we try and sort of exploit that resource more and more, we get more and more feedback. And this is one reason why, from my point of view, from what I'm talking about in the resource, it's really hard to do demonstrated projects, because if we're interested in total resource, we can't really do a demonstrated project without building a whole array. And then you've built a whole array. We can obviously do demonstrators of individual turbines, but actually some of these things only really occur, or some of the effects I'm talking about really only occur at scale. So let's think about how we might approach this. So if we don't put in any turbines in the flow, so I should say on the x-axis, we've essentially got the change of flow. So 0 means we've got naturally occurring flow. And as we move along the x-axis, we're getting less and less flow. And on the y-axis, we've got the amount of power we're getting out. So if we don't put any turbines in, don't get any power out. Equally, we could think of a hypothetical situation where we put in so many turbines that we completely stop the flow. Again, you don't get any power out. And so we could also think about some optimum where we're applying just the amount of right resistance to maximize the power that we're extracting. And so that's clearly a good upper limit to a site. But that's very much an upper limit. And we actually need to try and achieve these with real turbines. So what happens when we think about real turbines? We've got two different models, one more idealized, one slightly more realistic here. Doesn't really matter for my argument. So we can think about what happens when we put in one row of turbines. Well, we get so much power out, and then we try putting in another row of turbines, and we get a bit more power out. But we don't get twice the amount of power out because our flow slowed a bit. So every additional row of turbines we put in, we get a diminishing return. And it's really this diminishing return which really limits what the resource is of a particular site. But at some stage, it's going to become uneconomic to put in more rows of turbines because the incremental power is too small. And that's basic idea that we're trying to apply from this idealized scenario to more realistic things. There's also, of course, a big question about when you stop. When's the diminishing return not enough? I have some simplified arguments on that, but it's a really complicated question. So how can we improve this? Well, of course, what we are doing is we are improving our modeling, using more sophisticated models of the hydrodynamics. But actually, I don't think that's really the central problem to tackling this. I think it's really a multidisciplinary problem about how many turbines we can put in. And actually, this brings in a whole load of other disciplines that the environmental people need to tell us how much we can change the flow by and what's the impact on the sediment. There's clearly an economic question about how much extra power, how much each bit of extra predictable power is worth, and et cetera, et cetera. So it's a multidisciplinary problem, and that's to some extent holding up this analysis, and why really the analysis of tidal resource hasn't really moved on in the last 5 years or so. So to summarize, tidal power is predictable, but it is also intermittent. Tidal barrage, pretty mature technology. We know what to do. It's well understood, but there are some big downsides, and it's pretty difficult to do in a democracy. But there are lots of things that have occurred in democracies in the last few years, which have shaken my view of how things work in a democracy. Tidal stream, there's some more significant challenges, but we will be able to overcome these. But the big question is it actually worth it? And that's really, I think, down to how big the resource is. And that is at present an open question. So I will pause there and we will move on to our discussion.
Thank you very much, Tom. That was also well in time. So that was very good work. So now maybe the two speakers, you could stand, I think, to take questions and panel discussion. So I open the floor for questions. Maybe.
Yes. Yeah. Very interesting talk, Tom. And definitely we should talk more. But I see this possible synergy between tidal and wind offshore and solar and wind onshore. And basically, we have been doing modeling for several years in my group in terms of getting the optimal mix of renewable in a given geographical site. Because to an extent, solar is again intermittent, but quite predictable. Wind is not as predictable, but has other advantages. And there is, with historical data, you can actually optimize this. So do you, or are you looking at this complementarity between, in this case, streams in the ocean and wind? Because wind in the ocean is also, much better than.
It is, although I think, in fact, I plan to run a full YP on it next year. So if you want to co-supervise, we should perhaps do that before the deadline on Friday. And that, so it is something I think I'm becoming, I say, so it's not necessarily the main focus of my work at the moment, but it's something I'm interested in. And I think it's, I've got a bit fed up with people talking about tidal as a base load without actually, and I mean, I asked someone who presented this at a talk last week, has anyone ever done any calculation on this? And the answer was no. And I don't think it's a very hard calculation, to be honest. And so I think we should do it. And but it'd be, but actually, if you've got, I mean, it might well be that you're the right person to talk to help with that.
But looking at the pattern per two and.
Well, let's have a chat.
Thank you.
Okay, you had a question?
Yeah, thanks very much, Sarah, Tom. My name's Aaron Anstey from Anstey Energy. For the tidal question, tidal lagoons in, say, an area with a big tidal range is another option, I guess. But I have no idea, like, how much you would get from just a bay that you've got a tidal barrage in front of, rather than an estuary, or just like little lagoons, man-made lagoons within, where you've got a big tidal range in an estuary. Any idea of the outputs per unit, like meter squared or whatever what you get from that? Or has that been looked into at all? Or
So from my point of view, a lagoon is essentially very similar to a barrage in terms of technology. It just means you've got a slightly longer wall, and it's a slightly smaller scale thing. And indeed, if we are serious as a country about developing 7 barrage, probably what we should be doing is doing some demonstrators with lagoons, so doing some smaller things to try and understand that. And so I am a bit cautious. So I mean, there are estimates for the resource. I can't. If some of the sort of lagoons that have been suggested, and I'm not going to divide them 3 by meter squared in my head. But I think it is also important to actually treat some of the lagoon projects as demonstrators. That these shouldn't be that. So say the Swansea lagoon, which is obviously the one which would be done first, I think, in any scenario. But we should view this as a demonstrator, and we shouldn't be expecting it to wash its face. And yes, it's very expensive, but then most demonstrators are going to cost more than essentially the scaled up version. And so they're numbers out there, but that's what I'd say.
About you at the back there.
Thank you. Oh, thank you for both of your presentations, I suppose. So this is sort of to both of you in a way. Demand, I suppose, is sort of like key to sort of Tom's calculations then with respect to what he's looking to do in terms of the value, I suppose, of the tidal and how it matches up with that. But how do we actually get to what that demand profile is reliably then over a long period of time? At the moment, that's one very tricky to do, sort of, and my only way I can envisage doing it is sort of a bottom up. But at best, then sort of a lot of those vectors are just not provided, or sort of they're quite black box-esque in terms of we're just supposed to take it at face value that certain groups, say in London or elsewhere, then have done their business correctly and that it's reliable. But it sort of not only changes the results that you'd get, but even sort of the merit order in your methodology sometimes, then sort of attributing value to that. And just a minor one, do you think we should also consider sort of the system cost / benefits of these variable renewable energies rather than just the full load hour as well?
I mean, I work on demand. You know, I start from the position that you look at demand first, because the only reason we have an energy system in the first place is because we want to carry out certain things and we want energy to help us do that. But nonetheless, but having reliability and a degree of predictability about the supply is clearly an immensely helpful thing. And so, you know, a great thing about tidal is, as you say, you can be incredibly confident about where the moon is going to be, you know, 578 days from now or whatever.
We hope, yeah.
Yeah, in an uncertain world, that is really nice. And the tidal has something to offer there in as part of the mix that is incredibly valuable, and you want to count. So, I didn't quite understand what you were saying about that, though.
The demand profile.
The demand profile thing.
So I mean, if you were looking to sort of consider, I don't know, energy storage and what's needed, or you're looking to sort of contribute sort of on a more system design sort of way, sort of how much should I be willing to pay for tidal in order to pick it over another resource? I need to sort of know what I'm aiming at, rather than just in a system capacity, sort of a capacity market as we sort of currently have. So my question, I suppose, is what are those sort of profiles and how do we assess their dependability?
I guess I wouldn't want to take those as givens. I would want to say, how flexible can we make demand? You know, and then, you know, work from that.
But you could
but again, it's this shift from a demand-led system where you try and predict what the demand is, and then, you know, to a supply-led one where you say, well, this is the supply we've got available, guys. You know, you want electricity. How flexible are you prepared to make your demand? And And so you come at it from both ends, as it were.
I do think it's obviously sort of the point of having these meetings and of having an energy network, that there are all these different bits, both on demand and supply, which all need to feed in and interact, and that network is critical to all of them. And I guess that's why we have sessions like this, and why the network exists. So I think that's all I'll really say, that we all need to be better at talking to each other.
I think it's a very interesting question, because obviously with the increasing electrification of everything, predicting demand into the future is quite difficult. I mean, what is our demand going to be? And actually it is supply constrained. And actually, I think it's infrastructure constrained. Okay, you can have local energy networks, and I can put solar panels on my roof and all that sort of stuff. But actually transferring electricity around, even Oxford, we're reliant on the existing substation network. We're then reliant on the utility providers to improve that network. It's not cheap to improve the infrastructure in a already built out environment. And you can see actually quite a lot of challenges in the next 10 years if we really did want to move into a much more electrified system. How you can predict that, I think it's quite a challenge. I personally don't work on that area, but I can see there's a lot of interplay there. How quickly will SSE, for example, want to upgrade substations on the southern edge of Oxfordshire, where there's new housing supposed to be, and all this sort of stuff? I mean, who's going to put the money in? Because in the end, it is a money problem.
Yeah, I have a question to Sarah, I think on wheel. If this may be a social question, but I saw the map of solar potential or wind potential. But I'm from Japan. I think what I see in Japan is, that's great, but please don't put it on my neighborhood, because it doesn't look good, or I'm sure it depends on the person. Are you facing anything like that, or?
Not much, but it is. But there are certain areas which are conservation areas. There are special architectural interests, and so there you are quite constrained in what you can do. You have to be very careful. If you put solar on, it's not got to be visible from the street, for example, or from particular sight lines. Also, there may be constraints on what you can do to a building, in terms of the glazing or the insulation, external insulation, that sort of thing. So I would say it's predictable in that case. If it's in a conservation area, you would have challenges. Yeah, that would be the main thing. If you're outside that, on the whole, I don't think people mind. I would say on the whole, they don't mind that much.
Yeah.
Hi, I have a question regarding the tidal energy, that moving towards the zero carbon energy sources and the ancillary services that will be required in future. So with that tidal energy that you have just talked about, would that be able to provide any ancillary services in the system, and how much it would be in terms of the
clarify what you mean by ancillary.
like the frequency response or the inertia that is required in the service in the system, in the power system?
I'm not sure my electrical engineering is good enough to really comment on that. I guess I'm not sure actually. So whilst tidal is fundamentally predictable, there will certainly be fluctuations due to on timescales of minutes, due to large eddies, due to local weather, due to waves, and that probably limits the application, how good it is at actually responding to I guess to some extent those short-term things in terms of managing network. That would be my feeling on that. That said, I'm perhaps to expand the question slightly from your there are, so particularly on tidal barrages, there are clear whilst There are clear downsides to building a very large concrete wall. There are also upsides to that, particularly in terms of flood protection, which is something my group have looked at. We're due a really big coastal flood in the Bristol Channel, and a barrage would be a very good way of avoiding drowning Bristol. But on that there are some sort of connected advantages potentially, or you would try and manipulate the system so that it gives you those additional advantages, and that might be important in a business case, or at least in an environmental argument, weighing up pros and cons.
So maybe just to jump in, I guess it's similar to wind. I don't know what's the inertia like at the top. It's probably smaller inertia than a wind turbine, but obviously it's only going to be available mechanically when the thing is running, right? Which comes back to your point about variability. But I guess you could probably stick lots of capacitors in the electronics, and that might provide some inertia as well. Yeah, I mean, that's my
So
random.
do you presume it to be lower than the offshore wind or higher than that?
It's a very good question. My gut feeling is the inertia. I don't know. Looking at Tom,
Well, I guess
lower than a wind turbine.
yeah, the inertia, I guess, would be higher, and
Higher.
I think so, and the fluctuations would be lower. I mean, the force is a lot. The force divided by power is a lot larger. Density divided by U.
It's a very good question, actually. Someone needs to do the calc. We should.
But on a barrage, it would be actually on a barrage rather than tidal stream, it would be, because there you are much more in a position to play God on what's going through. And yeah, I mean, you could even use it to at least locally make very short-term balancing decisions there potentially.
Yes, I just wanted to ask you, because you said something about uses for storage.
I'm not sure but I can talk about
I
that.
thought you did. Use of tidal for storage, and I didn't quite get that. What's that?
So there are potential ways of, particularly for a barrage, of storing energy. It is. I have done some theoretical work to show this is possible on tidal stream, but I'm the first to say that that's not practical. Lots of beautiful Procboy soft paper explaining why that's possible in theory, but I also know only that you're playing essentially with the dynamics of the system. So if you slow the tide down enough, you can get some power a bit later.
It's quite short periods of time.
For a barrage, you do have a good bit of control on when you're generating, and you can also store energy through pumping, which is with an ideal pump, you get more energy back than you put in. With a real pump, it's a lot more marginal, but that certainly does mean there's appetite, and you certainly have some control with a barrage on that. And again, it's something I don't think it's certainly possible in theory, but what I've never really seen is anyone actually do the calculation in practice to say actually, yes, of course there's going to be some cost in total energy, but maybe there's a good trade-off there, that actually if we want to generate at least 7 a.m., 8 a.m. rather than 5 a.m. and 6 a.m. We could, I'm sure, and a barrage would be able to do that, to do a bit of energy, but it would be almost certainly be worth it. But it'd be very nice to do some calculations on that.
Yeah. Another question, Sarah. The map of the solar potentially in Oxford of those sites. Has there been anything done similar for like waste heat?
I would guess for waste heat. So you mean?
So it could be from an incinerator.
Yes, heat from waste. Like hardly. Yeah, I think they've got that done too. It's well worth taking a look at that set of work. Okay. They are covering heat as well, because future of heating, obviously, it's a major consideration. But also, yes, as you say, the use of it for generation.
Yeah, Please.
Can I ask a very specific question as a local resident? So I love your maps, and I live in Cumnor Village, and they're just, and I was smiling because your maps say, we're not going to put solar panels on farmland or in the greenbelt, and they're proposing to put up 2 big solar farms next to us in Cumnor on greenbelt and farmland. So is there a disconnect between what's actually happening and this theory, and how can we stop that? Well, I should say I'm all in favour of them regardless, but I'm just interested.
Well, there would seem to be. And I can only say, the county council are the people who are, the planning authority. So that would seem to be an issue to take up with them, really. If you wanted to take it up.
They're just not yet using your stuff.
Pass.
They haven't yet got permission, have they? So they've put in an application.
But it seems weird that they would even do it. I mean, we've got all this stuff, why don't we just use it?
Maybe. I mean, people do lots of things which you think maybe not sensible.
People have a go, to challenge that, I guess. They might well. Similarly, there's been an ordinance that you cut in central Oxford, if you're in a listed building, you can't double glaze your windows. And, people have, and there was quite a successful challenge mounted over that, I remember. I think it was by Christopher Ball of Keighley College and his wife. Why on earth can we not retrofit our house and try and get it fit for the future? And
is the Leo project, are you also looking at, or have you looked at, what council government can do for incentives to ensure to get people doing things? Because there was a lot of incentive a while ago for solar panels. There was a huge number of panels going up on the roofs of houses. Then the incentive stopped, and they all stopped. Yeah, and that seemed a bit of a
interesting. I mean, one of my colleagues, decided, I don't think how that being a researcher on endless fixed term contracts, was perhaps what he didn't want to do for the rest of his life, and he became he runs a very successful solar company. And, the feed-in tariff came to an end, and I was thinking, well, Chris, he's got more business than he's ever had, actually. But it's a different sort of thing now. It's a combination of solar, EV, charger, battery. Okay. And the appeal, which doesn't make economic sense, but makes a lot of kind of emotional sense to a lot of people, is feeling they're fairly self-sufficient. So,
a bit like Britain wants to be now with the gas price.
I can comment on that because I'm actually thinking of doing it on my own house. Yeah. I think the marginal cost of adding solar, if you're doing something like a loft conversion, is pretty small.
Yes.
So, I mean, loads of people on our street are doing it. I think this is. I mean, we're looking at the news. This is happening all over the country. It's kind of a no-brainer.
Yes, and it's taking a holistic view, and it's seizing the moment that you're doing your house up anyway. So, yeah.
I actually wanted to ask Tom about sorry, I know it's lunch. You had a graph of wiggles, and I was just interested in from a sort of storage point of view. We know that there's this anecdote in wind that the UK has every year a kind of, I can't remember the exact number, but like a 3-week wind calm period. Is there do you have a number for tidal? What's the kind of period that you have to ride through if you had a huge tidal system?
I mean, that's a spring meet cycle, so it's a 14-day cycle, so essentially 7 days to get across half of it. And again, that's unlike the wind side, which I do have a student looking at exactly those lulls at the moment on the wind side. But obviously, at least you know what it is, and you know when it is, and you know when it's going to end, which is also quite helpful in terms of doing if you're in the middle of it. Great.
But when it's stormy, I mean, in the stormy seasons, does that mess things up? You get less.
Well, the impact of waves on tidal is, I think, shall we say, an open question, which my colleague Richard Wilden is looking at more. Although because I really do waves. That's something I'm involved in. Not wave energy, but wave loading. I think any system you designed, you would try and put the turbine. You would try and make sure that waves weren't a big thing. So they're two basic. You can either have a floating turbine where it is quite vulnerable to waves, but by definition, you're probably going to put that at a site which isn't very exposed to waves, or you can mount your turbines on the sea floor, in which case you probably design them to be a bit lower in the water column. So waves, they're still going to be a bit of an issue on both the loading, but it's not going to be a huge issue.
Okay, final question before lunch. We've gone a little bit over, but that's fine because it's a good discussion. Yeah.
Just a brief follow-up, sort of similar to sort of wind. It also has substantial sort of wind droughts that occur sort of in sort of various periods of like 15, 20 years across the UK at least. Is there anything, I can't think of a reason, but is there anything like that that would affect tidal?
So I'm not sure. So I mean, there's certainly, I mean, interannual changes in wind. What the North Atlantic Oscillation is doing is pretty important to the wind resource. There is an 18.6-year cycle with in the tidal system, and that's not in and that so whether you're with the peak of that was about a year ago, and I mean it depends very much how you do the calculation, but the resource is probably going to be 10-15% better than halfway through that 18.6-year cycle in 9 and a bit years time, when because of the second order things in terms of the planetary movements, the tides are all a bit lower. So there are, I mean, there are even longer term cycles, but that's the main longer term one. There's also, tides are bigger at the equinoxes, which and so there's also an annual one. But these things, these are basically known.
Okay, great. Well, I think we should just show our appreciation to the speakers. I'm sure there's still lunch left.